Hello and welcome to video number 6. Today we'll talk about excitation and performing experiments. So we will try to answer the question, what input should we send into our system when we gather data so that we get an informative or exciting experiment. And I say exciting here, it has a particular meaning in system identification, which we will dig into in this video. All right, so first we'll start with, there is a theoretical concept called persistence of excitation. So that's roughly equivalent to if we would form a large correlation matrix of the input signal, what rank would that correlation matrix have? And so that's very a loose definition. But it gives a rough indication of how complicated models we are able to estimate using the input signal we have used. So you can roughly think of it as proportional to the number of parameters you can estimate, but that's not quite true. Okay, so this is a theoretical concept. We will try to make that a bit more practical during the rest of the video here. So for linear time invariant systems, they have this very nice property that if we know the impulse response of the system, then we know everything there is to know about the system. And likewise, if we know the frequency response of the system, we also know everything there is to know about the system. And that's of course because the frequency response is the Laplace transform of the impulse response. So what is an impulse response? We see two impulse responses here. There are two different systems that we have passed an impulse into. So the impulse response is exactly what the name implies, is how the system responds to an impulsive input. So if our input u is given by the Dirac delta function here. And that's kind of, you notice immediately that that's kind of problematic because the Dirac delta function is infinitely large in amplitude, but it has kind of an infinitesimal duration, such that if you integrate it, the area is 1. And it's nice in the sense that the spectrum of this delta function is completely flat, so it has all frequencies present in one single impulse. So it's persistently exciting of any order. It allows us to estimate any arbitrarily complex linear system. But it's of course impossible to realize a theoretical impulse. You can't send an infinitely large signal into any system really. So in practice we kind of approximate this theoretical impulse with a practical impulse that has a large but finite amplitude and a very short duration. But even such practical impulses might of course damage a system. For instance, practically occurring impulse response experiments involve, if it's a mechanical system, maybe it involves you hit the system with a hammer to excite the system. And some systems tolerate the hammer blow, whereas others, of course, do not. All right. Another drawback with an impulse response experiment is that you have a very high sensitivity to the first few samples of your data. So if we look at the impulse response of plant 1 here, it's a first order system. It immediately starts at 1 here. And if you collect this impulse response with some noise, you will have get a very poor model of the system. So these first few samples are extremely important for the model of the system we'll get out of the estimation. So for instance, in acoustics, impulse response experiments are very common. But what you do there is typically that you perform the same impulse response experiment multiple times over. And then you kind of average the result there. And for acoustics, maybe you can realize the impulse by popping a balloon or shooting with a gun to create an explosive. So that's kind of an impulse. But you can also send an impulse to your speakers, perhaps, and you will record the reverberation of the room you're in or something like that. All right, so impulses are theoretically nice, but practically sometimes quite difficult to make use of. They're also used in medicine, where if you inject the patient with An injection, that's like an impulsive input. That is okay in many times, and that's in fact how we inject a lot of medicine. All right, another kind of excitation is when we perform frequency response experiments. So here we show a frequency response function of the two systems we looked at before, P1 and P2, and I've indicated here with dots, so that those dots kind of imply that we have measured the frequency response in these points. All right, so how can we do that? So we know that if we send a sinusoid into a linear system G, that sinusoid will come out with the same frequency on the output, but it might have a different amplitude and a different phase. So if we record the difference in amplitude, we call that difference K. It's the ratio of the amplitude in the output to the amplitude in the input. And we record the difference in phase, delta phi. Then we have actually exactly measured G in one particular frequency. Right? So if we do that for multiple different frequencies, omega, that would allow us to plot the Bode plot immediately. All right, so then we have kind of a non-parametric model of our plant. We can't give it like a small number of parameters that describe the system, but we can plot the Bode curve or the Nyquist curve or the Nichols chart, something like that. So that's one way to estimate the model. We can also send multiple sine waves with different frequencies at the same time. Okay, and that's an experiment that is persistently exciting of order 2 times the number of sine waves. All right. And the third kind of a frequency response experiment that I'm particularly fond of is a chirp experiment. All right. And a chirp, we will see a chirp later, is a kind of a sinusoid that has an increasing or decreasing frequency. So it's like a bird that is chirping. All right. So just a note about amplitude here. A linear system doesn't care about the amplitude you pass in. If you double the amplitude, you just double double the amplitude of the input, you just double the amplitude of the output. But if you increase the amplitude of the input so that the output increases, typically you improve your signal to noise ratio, because the measurement noise is typically independent of the input you use. So you can use a larger amplitude to improve signal to noise ratio, and that's a nice thing. But if you use too large amplitude, then maybe you risk exciting some nonlinearities that you don't want to actually model, or you might destroy the system, of course, if you use too large amplitude. And that's, of course, a drawback. So in practice, it's always a trade-off. All right, so here we see an example of a multi-sine experiment. So here we have some input, consists of 3 different sine waves and the corresponding output here. And here I show the spectra of the input and the output, and we see it's actually 4 different sine waves. There are 4 peaks. This spectra is, of course, an estimate. So the true spectrum has only 4 signals, 4 peaks, and it should be 0 everywhere else. But since we have estimated this from the data, we have some spectral leakage. We have estimated this with the Welsh spectral estimate here. But the transfer function here is the ratio between the spectrum of the input and the spectrum of the output, or the opposite of that actually, the output over the input. So this would allow us to estimate the transfer function in 4 distinct points. All right, and here we see the code for that. We don't really need to go into that. We can just note that to plot this, if we have an identification data object, we can plot the Welsh spectral estimate of the input and output by calling Welsh plot. All right, here we have a function that creates a chirp. It takes in a sample interval, initial frequency, final frequency, and duration, t final. And then it creates an exponential chirp, so it has an exponentially increasing frequency. And we perform an experiment here with a chirp, and we plot that result. So here we see the output of the 2 systems, P1 and P2, and we see one of them, the red one, it just decreases with time, whereas the orange one kind of appears to have some kind of resonance here for a particular input frequency. And on the right side we show the spectra for the P2 system. So we see that the input has a relatively flat spectrum, but the output has been shaped by the frequency response of the input. We also see that since the chirp started here at half radian per second and ended at 10 radians per second, we see that the input has a high power for starting at some frequency. This plot is actually in hertz here. So it starts at 0.1 hertz and it goes up to about, I don't know what this is, 5 hertz or something like that. And outside of that we have almost no power in the input signal. So and that also goes for the output, right? The output doesn't have any power outside of the range of the chirp. So if we try to estimate the model using this data, we can't really rely on that model for very high frequencies because we haven't actually excited the system at those high frequencies. Right. We can also plot a spectrogram. So a spectrogram is similar to a Welsh spectral estimate, but we perform it in over small chunks of time. So we plot here, we have time on the x-axis and we have the frequency response on the y-axis, or the frequency axis on the y-axis, and then the frequency response is encoded in color here. So we see that the chirp has a, if we plot it on a logarithmic frequency axis, since it was an exponential chirp, we get a linear increase in frequency. And we get the corresponding linear increase in the output. All right, and we can plot that figure by calling something called spec plot for spectrogram plot. All right, if we observe something like this, so we pass a chirp as our input, and out we get not only one frequency, but we get two frequency bands here. Okay, so that's an indication that the system is nonlinear. Typically this second frequency band occurs at an odd multiple of the base frequency. Maybe there can even be multiple odd multipliers of the base frequency. So that would be an indication that the true system, the system you're identifying, is not actually linear. And if we plot something called the coherence plot, all right, so we will go into a bit more deeper what that means later. It's an indication for each frequency how well a linear model describes the data. Okay, so the linear experiment up here, we had a high coherence, close to 1, for the entire duration of the chirp. But this second experiment here, where there appears to be a nonlinearity, so this is a different system, that has a drop in coherence for certain frequencies, so the coherence is very low, indicating that a linear model is not a good explanation of this data. Right, so the coherence function is something that is quite useful to plot before we estimate any model, to figure out is a linear model a good description of this data. All right, so I said that I happen to like the chirp excitation particularly much, and I tried to show why in this little animation here. So imagine that you have a mechanical system, or any system where you can somehow see the response of the system. If you apply a chirp, you actually see the frequency response unfold in front of your eyes. So here we see as the frequency increases, we see that at this point we got a resonance. And we can associate that by looking at the process. Maybe it makes some noise there. Maybe we can see it swinging violently back and forth and so on. And that allows you to iterate on the shape of your excitation very quickly. Maybe you realize that now this amplitude is too large because now I heard some noise from the system and I need to decrease the amplitude in a particular frequency range or something like that. So this is a nice and intuitively useful excitation signal. Of course, if the dynamics of your system is very slow, for instance, hours or days, then of course this is not as useful. Or if you can't see the frequency response, maybe maybe you're dealing with a thermal system and you can't really see it, you can only see plots, then it's less useful. All right. Another kind of signal we can use is a random signal. So we can try to use white noise, and that's very nice because it has a flat spectrum. It's persistently exciting of any order. So here we see on the left hand side in the plot, we see some Gaussian white noise. So the input is the bottom here, and we see the output in the top. All right. We can also make use of colored noise. So that's, you can think of that as a white noise that has been filtered to have a particular frequency response. That's nice because then you can focus your energy in the input on certain frequency ranges where you're interested in having a good model. You can also use a random binary sequence. That's also nice. It's persistently exciting of any order. And another benefit is that the binary sequence has the lowest possible crest factor. Okay, so that's a term, you can read about it in the book by Leonard Jung, System Identification Theory for the User. Essentially, it means that you get a large power with a small amplitude. Right, so we see a binary data set here on the right. We see that the output of the system is roughly of the same magnitude in both cases. But we see that the amplitude of the binary signal is never above ±1, whereas the amplitude of the Gaussian signal here reaches above actually -3 here, right? So if you are worried about sending too large amplitude inputs into your system, then a binary signal might be more reasonable. All right, so a particular way you can create the binary signal is just to take, if you draw a random noise, so this is a Gaussian signal, Gaussian random noise. If you take the sign of that, you now get the signal that is between ±1. So that's a nice trick. All right, we can also have a look at the spectrum of this signal and the spectrum of that signal. And we do that here by calling Welsh plot with the identification data. And we see that the spectrum of the input is flat. Okay, so that's an indication that this is white noise. And that's indeed what white noise means. White light that is coming to us from the sun, it contains all frequencies. Okay, so the spectrum from the sun is not actually flat, but we interpret that as white because that's how humans are built. So white means that it contains all frequencies in this case. And we see that the output then has a different frequency response. The output has, or sorry, a different spectrum. The output is colored by the frequency response of the system. Right, so if we see a spectrum of the output like this where the input is flat, we can actually immediately see the transfer function of the system. So the transfer function is the ratio between the output and the input, and since the input is flat, the transfer function is just a scaled multiple of the output spectrum. All right. We can also perform step response experiments. Those are quite common in practice. A step response is dominated by low frequencies, or sorry, a step input is dominated by low frequencies. The transfer function, or the Laplace transform for a step, is 1/s. So that is very, very large at low frequencies and almost nothing at high frequencies. And I say here, I indicate here that that can be both good and bad depending on what kind of model we want. All right. It's persistently exciting of order 1, so that's very poor excitation. It doesn't allow us to estimate very interesting models. But a benefit is that the step response experiment is very easy to perform. For a lot of systems that occur in practice, maybe it just means that you have to press a single button. Okay, change the reference from 1 to 2. Okay, and that's a step response experiment. Another benefit is that you can fit a simple model by just looking at the the step response. So here, the step response of system P1, we see that that has this is a unit step, so the size of the step is 1. And we see that the static gain is 1, and we can see that the time constant here is also roughly 1. All right, so that should immediately tells us a reasonable transfer function model for this system. But we see here the input here is completely flat at 1. So there is not much happening in the input, so we can't expect to fit any reasonably accurate models that model the input dynamics. All right, so then we have a note on closed loop data. So until now we have just assumed that we can send any arbitrary signal into the system, and very often we cannot do that. Maybe the system is unstable, so if we just send random noise into the system, it will crash and burn. So imagine a quadcopter. We would not get very interesting data if we send random noise into that. And another alternative then is that we have a controller that is controlling the system, and we look at the input the controller sends into the system and the output that produces. That will lead to the input being correlated with both the noise, the measurement noise, since the input is a function of the output that contains noise, and the input is obviously also correlated to the output. And there are lots of identification methods that become biased in this setting, so we should be aware of that and be careful. The prediction error method is unbiased, but it's one of few methods that actually are unbiased. What we can do in this case is we can try to break the correlation by either modifying the reference to the controller, or we can add some additional disturbance here to the input. So if we look at the closed loop system here, we try to identify P, and C here is determining the control input. But if we change the reference here, we will get some exciting signal here. And if we add some additional disturbance here, we will also get sufficiently exciting input. So if we take the quad rotor here, maybe D is some disturbance. It can't be too large because then the quadcopter will crash, but maybe it's acceptable to have some small random disturbance here. So we will look a bit more detail on why closed loop identification is difficult for a very simple model. So here we have a very simple first order system in discrete time that says that the output in the next time step is a linear function of the current output and the current input. And now we introduce the feedback controller here, so saying the input is negative k times the output. Right? So if I insert this expression for u in this equation here, we now get y plus is ay minus bky, and we can simplify that, and we see that now we have now the y in the next time step is depending on only y in the current time step. And we see that the parameter here is a minus bk, and that means that we cannot from data collected here tell the difference between a and b. We can only identify the combined parameter a minus bk. So we have lost identifiability of this simple system. So in video 2 we were looking at an ARX22 model. So that means a discrete time transfer function with two coefficients to estimate in the numerator and denominator. And we said that we could arrange the data for such a model on a matrix form, where we have a regressor matrix phi and some parameters w. And that regressor matrix looked like this. So we had y, and then we had y one time step back, and then we had u and u one time step back. If u now is equal to a multiple times y, then we see that this column will be linearly dependent on this first column. Okay, so instead of a rank 4, this matrix will now only have rank 2. So when we try to form this estimate here, we cannot invert phi transpose times phi because it has rank 2 and it's a 4x4 matrix. So that's another indication that closed loop identification can sometimes be difficult. However, if we add some excitation through R, so if we change this reference up here, then how does this simple model look? Then we say now u is k times the difference r minus y. All right, and then we, after some simplification, we obtain this equation here. So now we see that we have two different parameters that we can identify. We can identify bk, the combined parameter bk, and a minus bk. So if we know k, then we can compute b from that. And then since we have estimated the bk, we can compute a from that. So now we have recovered identifiability of a and b. And the same analysis here if we add excitation through d. Then we have this system model, and we have the simple controller without any reference. And once again, we are able to estimate b, provided that we know the disturbance we added. But since we added it ourselves, that's okay. We can identify b. And then from b, we can compute a. All right, so in closed loop, we should be careful to make sure that we get good identifiability of our parameters. All right, so far we have been talking about linear systems. Not all systems are linear. In fact, almost no systems are truly linear, even though we might be well off approximating them as linear in some cases. So I said before that linear systems, they don't care about the amplitude you pass in. But nonlinear systems certainly do. So you can detect whether or not you have a significant nonlinearity in your system by performing the same experiment twice, but with different amplitude. So ideally, if you double the amplitude of the input, the amplitude of the output should also double. And if it doesn't do that, then there is a sign that we have some nonlinearity. You can also perform the same experiment in reverse. So for instance, if you have a chirp that goes from low to high frequencies, you can also apply the same chirp but from high to low frequencies instead. And that should give you the same frequency response for a linear system. But for nonlinear systems, that might not be the case. So excitation for nonlinear systems is a very complicated topic, and it depends extremely much on the particular system you have at hand, what is a reasonable excitation. Sometimes a good rule of thumb is that you should try to excite the system in roughly the way you want to use the resulting model, but that's obviously very loosely speaking. So here we have an example, and here we have performed a step response where the step is size 1, so a unit amplitude, and we see that in red. And if we do the same experiment, but the step is of size 2, and we get that in orange here, we see that the orange curve is not just twice the red curve. Twice the red curve would have been the green curve. So if we had observed the green curve here, then we could say, oh, okay, we didn't detect any nonlinearity with this experiment. But if we observe the orange curve, we see that, yeah, there is probably some nonlinearity in this system because I didn't get the double of the twice the response. So that's kind of an easy trick to try to detect nonlinearity. All right, the last topic we'll talk about is how do we evaluate the identification data we have obtained to see if it's any good for system identification. So we have already looked at the spectral properties of the input. So we can plot the spectrum of the input, and for frequencies where the input contains a lot of energy, there we might be able to estimate a model of the system. But for frequencies where that are not present in the input, then we can't estimate a model that is accurate for those frequencies. We can also have a look at something called the magnitude squared coherence. I call it here kappa squared. So we have seen the coherence function previously, but we will go into a bit more detail now what it means. And we can also look at the covariance matrix of the data. And here, when I say the data, I mean the kind of a regressor matrix like phi we have looked at before. And if that is well conditioned for the size of the model we want to estimate, that means we're good to go. If it's ill conditioned or if it loses rank, that means that our identification data is too poor. All right, so the magnitude square coherence. It's a function of frequency. All right, so if we have a signal model that looks like the output is a linear system times the input plus some noise. Then the magnitude square coherence is defined as the cross spectrum SUY, so the cross spectrum between the input and the output, divided by the auto spectra of the input and the output. All right, so we can rewrite that using some simple formulas for power spectral densities into an intermediate step, and then we can arrive at a last step here. And this step is illustrative because it shows immediately that the magnitude square coherence is always between 0 and 1, all right? And it's close to 1 if the noise power spectral density is very small. So SVV here is the power spectral density of the noise that acts on the system. So if that is very small, it means that this whole term is very small. It means that the magnitude square coherence is 1. However, if the noise is very large, then this denominator is very large, and then we get the coherence close to 0. And the noise here can be either traditional noise, like measurement noise, but it can also be anything that doesn't fit with a linear model. So if the true system is in fact nonlinear, then G times U here, the transfer function G, doesn't capture the data. Then we would have to associate some of that output data to noise, and then we would also get a low coherence. So the coherence function is kind of a nice and easy to use non-parametric method to figure out if your data is good. So here we see an example. I have applied a chirp from frequency 0.5 to frequency 10. And then I have added a periodic disturbance to the output, so kind of like a measurement noise with frequency 2 radians per second. And we see that the coherence function for this data, it's large between the frequencies included in the chirp, so 0.5 to 10. But at this particular frequency 2, where the disturbance acts, we have a very low coherence. So when we see this coherence function, we say that, yeah, if I estimate a model using this data, that model will probably be good between 0.5 and 10 radians per second, but it will potentially be poor at around 2 radians per second. And below 0.5 radians per second or above 10 radians per second, I can't trust the data because I haven't actually sent any signal in there. And we see the spectra here for the input and output. And once again, the input is relatively flat, and it's large. The power spectral density is large in the frequency range covered by the chirp. And then we see how that has been colored in the output, so colored by the frequency response of the system. So very often, at least for single input, single output systems, before I estimate any model, I always look at this coherence function. All right, then the last step, we can look at the data covariance matrix, so this regressor matrix for an ARX model. So if we perform an experiment like this, it's a step response experiment. So the input starts at 0 and then goes to 1 and stays there for all eternity. All right. So I have just simulated that system here, and then I call this function getARXRegressor. So that gives us the matrix phi. Then I compute the singular values of that and also just the rank. And we see that this matrix now, we have 2 coefficients in the denominator and 2 in the numerator. So that gives us a regressor matrix of size 4, or of width 4. So it has 4 singular values, 3 of which are relatively large, 1 of which is tiny. All right, so the rank is 3. So I can't actually invert this matrix to form an estimate of such a model. And if I try to increase the number of parameters I estimate, so say that I want to estimate a 6th order transfer function, then we see that the rank of this matrix is still 3. All right, so now we have 3 large singular values, and then we have all of the rest of them are tiny. So that means that the data is not good enough to fit such a large model. The only model we could estimate using this data would be, let's see here, could we estimate, we should know what kind of model we can estimate. we should be able to estimate, so 2D P1. If we discretize the system P1, see that we have one coefficient in the denominator and one coefficient in the numerator. So if we say 1, 1 here, we get a matrix with rank 2. We could actually try to increase that, and we might actually be able to, in this case, estimate the model with the 2 coefficients in the denominator. All right, so to summarize, we have been talking about how we design the input to our system so that we get an experimental data set that is informative enough to actually compute or estimate a model of the system. All right, thanks.